All right, so thanks everybody for coming to our Mage tutorial session here today. You're going to get really sick of me talking or listening to me talk because I'm the person that you're going to hear talking to you for the next roughly 2 hours. But it's designed to be a hands-on tutorial session. We've got a bunch of opportunities for you to actually get your hands dirty and play with the data that we've produced from the model. So it won't be hopefully quite that painful. Before I get started and go too deep down into it, let me just do a quick introduction for myself. I'm Mike Wolperger. I'm the Deputy Director for the Center for Geospace Storms, and I'm the one who's standing up here today talking to you about the MAGE model and all the great capabilities that has. But I'm just the bright, shiny face representing a really, really amazing team of folks that have made major efforts here. And there are a bunch of them in the room and out there that I want to make a moment of introductions for. So I'm probably going to do the Academy Award thing and forget somebody, so somebody will get me afterwards for doing that. Slava Merkin is the PI of our effort. He's done a really great job of leading this team. We've had great contributions from my brain trust down here: Anthony, Dong, Shen, Nikhil, Kareem. Let's see, who am I forgetting? Let me go through my model side. Honan and Kevin, and let's see. Adam, yep, thank you. Anyway, if you're on the MAGE development team, raise your hand so we can all give you guys a round of applause for all the work that you did putting this together. So thanks a lot for all the effort that came into it. We, on the modeling side, view this almost as our CubeSat delivery. We've been working really hard, pushing right up to the last minute to get it ready for delivery and push it out there for you today. So we're super excited to make that available to the system, to you in the team. So what are we going to do here today? I'm going to spend roughly the initial third of the time frame giving you a little bit of background about what MAGE is, what are the components that come into MAGE, and what are the capabilities that come along with that. And then we'll dive in and get that down and dirty with installing and running MAGE. I didn't have enough time, I didn't have enough bandwidth to be able to figure out a way to get everybody onto a supercomputer so that you could be able to do this in real time going along with it. So this portion will be a little bit of a follow along, a guide through our documentation, but then we'll also provide some other pathways for getting at it. And then the last portion of the presentation will cover hands-on tutorials with our analysis packages, ChiPy and GCM ProcPy. And that I was able to figure out how to actually be able to get you to be able to do that hands-on. And we have Google Colab notebooks for both of those things that people will be able to use and do access to the data, so that once you complete the install and run steps, you can use our tools to do analysis and going into it from that side. And I say I there, and I really should say we. It's the effort of a lot of folks on the MAGE team, development team, that have been doing that forward. So a little bit of vernacular, a little bit of terminology. MAGE stands for the Multiscale Atmosphere Geospace Environment Model, and it is a modeling suite that brings together a variety of models for different regions of the geospace system to do simulations. And we're basically using different version numbers to go forward with that, to talk about the different levels of model complexity, different levels of model regions of space that are covered. The first version of the model that we released last year and have made available to the community through the CCMC is MAGE version 0.75, and that just covers the geospace environment. It has the Gamera model for the magnetosphere, the remix model for the high-latitude ionospheric electrodynamic coupling, and the Rice convection model for the inner magnetosphere. And right now, that's only available via runs on requests at the CCMC. That model has been up at the CCMC for at least a year, maybe two. It has hundreds of runs, a fair amount of stuff that's available, very robust engagement going on at CCMC. Just this week, we have been working closely with the CCMC folks and have turned on Mage version 1.0. The major addition here with Mage version 1.0 is the addition of the TIGCM model for doing the ionosphere-thermosphere coupling. That's available for the runs on request. You can use it for science production, science quality analysis. We do recommend that you follow the CCMC rules of the road and reach out to us before working on doing a publication, just so we make sure that you're not publishing some weird anomalous feature of the startup or the configuration, that you're getting good science quality data out of the system itself. That has the Rice convection model for the inner magnetosphere. We've tested, and we think that that's a robust system, so that's ready to go for folks to start doing science quality, science ready results with it from there. That version of the model we are not releasing as an open source product, primarily because of some issues that we encountered with the legacy code that's embedded in the RCM, in particular the Clawpack package we don't have the authority to release that as an open source model. So what we are releasing as the open source model, and I'm going to spend the vast majority of the rest of this presentation talking about, is what we're calling Mage version 1.25. And for 1.25, what we've done, or what I should say Anthony and Kareem have done, is developed a new inner magnetosphere model. They're calling it RIGU. I can never remember what RIGU stands for, but they acronymed it somehow, right? Very clever, yeah. So ask Anthony afterwards. He'll give you the very clever background. I think it's J and U for the bounce averaged and the inner magnetosphere. Anyway, that model is essentially a complete rewrite of the RCM, not using that Clawpack technology, using the underlying numerical technology that we use within Gamera. We have also developed an integrated run and build system for the whole suite of models that has been extensively tested on the NSF NCAR derecho platform and the NASA high-end computing Pleiades platform. So if you have an NSF grant or a NASA grant and you want to use these things for doing science, you can ask for time on there. And then our suite of tools and things that I'll talk to you about here today will work on those systems. You can run this on smaller systems if you got your own cluster. You could do a toy problem on your laptop, but we're not providing the detailed instructions at this time for all the different systems out there. It's just a complicated suite of libraries and compilers and whatnot that would be too tricky for us to do at this moment in time. But we are providing robust instructions for the common high-performance computing platforms that are available to the community. The model is designed and intended to be run in high-resolution modes that allows you to go after those mesoscale features and look at that coupling across the regions and physical domain scales that comes into play. I mentioned that it has the TIGCM as the thermosphere-ionosphere model. That is TIGCM version 3.0. Honan Wu from our team has been leading an effort on the modernization of TIGCM, drawing on the skills of numerous folks, Winbin, Kevin, Dong, Nikhil, for getting that going for the ionosphere-thermosphere. Honan has a new publication out on TIGCM 3.0 that's currently under review at JGR, and I keep getting alerts that people like that paper because I think it's got already over 100 reads as a preprint, so that's available for you to do that, as well as it's truly open source now. The GitHub repository is open and available for people to do that going forward with it. And the last piece that's on this slide for me to talk a little bit about is the suite of analysis and visualization tools, the ChiPy and GCM ProcPy, that we're going to spend a lot of time here at the end of the session talking about and working our way through there. So I thought I'd spend just a few moments talking about each of the component models that come up to making the Mage suite a possibility for going forward with it. The core backbone of the system is the Gamera model, grid agnostic MHD exascale ready applications, I think is the backronym on Gamera for what goes on there. For those of you that know me or have heard me talk before, that is a building on the numerical legacy and development work of the Lionfetter Mowbray code, the LFM MHD model. That's one of the pictures that made when I was a grad student in the upper left there that still looks pretty kind of cool, but we're building on that LFM numerical technology. It is being able to solve the MHD equations on arbitrary hexahedral grids with face-centered and cell-centered coordinates to do all the modern shock captioning processes to allow you to be able to simulate a system as complicated as the magnetosphere. One of the successes of our group and the efforts on this is a paper led by Binzhen Zhang, who was a graduate student at Dartmouth and then spent some postdoc time with me at NCAR before going over to Hong Kong University in China. He and Kareem did what I never was successful in doing, and basically were able to download all of John's knowledge about doing MHD model coding and wrote a paper summarizing that all up, and it's in app.js, the application of the LFM numerical technology, all of these standard tests and analyses that you want to be able to do, why we think using a higher order method is a computationally efficient way to get really good scale resolving capabilities. And so if you want to know more about the numerics behind the MHD solver, and actually these are the same numerics that are buried in Raiju, that is a really good paper to go after with it from there. The rewrite of the Fortran of it into Fortran is modern Fortran, so it's using the sort of object-oriented nature of Fortran, but still using Fortran for the formula translation portion of it to be able to do really efficient, high-performance computing on modern computing platforms to come into play. I'm reminded of a joke that John told me when I was just a grad student, which is that he can write Fortran badly in whatever language you give him. So we're trying to write, actual Fortran in Fortran, but the techniques that go into play there. Gamera is an MHD solver. We are using it in the MAGE model as the MHD solver for the magnetospheric portion of the Geospace simulation, but it has been applied and used for other studies. There are simulations and work that's been done for Venus. Jupiter is a particularly interesting example to look at. And notably, that numerical technology can also be applied for doing the calculation for the heliosphere. What happens when you go from the 20 RS to the 1 AU domain, and you can use that, and you get all the shock capturing and advanced numerical techniques that come into play that can be super interesting for the evolution of CMEs out into the system. The next piece of the MAGE modeling system is the Raiju model. This is the newest member of the MAGE family. This is work that Anthony has been leading with lots of help from Kareem and other members on the team, developing that rewrite of the RCM approach. It's still solving the fundamental RCM type of equations. It's not a new physics. It's just a new numerical approach for it in modern Fortran with the shock capturing technologies and systems that are designed to work on spherical grids and pushing forward with it on that front. Here are a few quick images that you can see from the initial results there of where the computational domain that's being solved in the system itself, and the overlapping regions of the plasmasphere and the ring current and whatnot that come into play, and importantly how those things are going to map down into the auroral zone and come after that capturing there. We're trying to use the capabilities of Raiju and those pieces to help improve the auroral modeling, which I'll come back to in just a second. Oh, wow, one of them's a movie. I didn't realize it was a movie. Cool, look at that. You can see it evolve and going forward, and the structures that you see at the interface there along the magnetopause boundary that comes into play. Oh, this one's a movie too. Wow, cool. All right, great. So the other piece of the technology that comes into play here is the remixed model, the global electrodynamics solver, and this is what's essentially taking, as is illustrated in that middle panel, the currents that are at the inner boundary and mapping them down along the field lines to the high latitude region, and then solving the current continuity equation to give you the cross-polar cap potential and the evolution of what those field line currents are going to look like as it's going forward there. Remix has been effort that's been led by Slava Merkin during that solve for the high latitude things, and becomes part of the essential coupling to the TIGCM. The TIGCM wants that high latitude potential region to be solving for the global electric potential. Eventually, this will get replaced with a global 3D solver, but this is what the MAGE 1.0 and greater have in there for the system going forward. One of the key things that you need to be able to do to solve the high latitude electrodynamic equation is to know what the conductivity is in that region. And Donglin and Shenshen Bao have been doing a lot of really great work on the development of what we're calling the Dragon Kig model, which is trying to take that information that we have from models like Raiju or the RCM about where the plasmasphere is, where the different energy populations of the plasma are in the inner magnetosphere, and using what we call gray box modeling to say, okay, we know that this is where the chorus waves are going to be corresponding to this plasma distribution. So let's use that to introduce those processes to give us a diffuse auroral precipitation into a particular region in there, and then have that region evolve dynamically as the distribution of plasma in the inner magnetosphere changes. It also has the ability to do the monoenergetic electron, all of the night-like relationships that are kind of familiar to us going forward with that piece coming from there, and the capability for us to add new precipitation models as we go along. Cusp precipitation, broadband precipitation, other processes that come into play, proton aurora. One of the things that you'll see in our terminology is that we have a repository called Kaiju, because we're all a bunch of geeky, nerdy people going back to John's love for old Japanese horror movies. And Kaiju is the Japanese term for the Godzilla and Gamera and those kinds of things. And Dong has brought in the influences from his culture, and we now have a bunch of, Dong and Shenshen, thank you, have brought in the influences from their culture, and we have a bunch of connections to the different Chinese dragon gods that come into play. There's a great slide on that coming forward there, so trying to expand the scope of what we're going after with that perspective. Okay. And then the last model in the suite that comes into play is the TIGCM, the thermosphere-ionosphere general circulation model. That, as I mentioned, TIGCM 3.0 has just recently been released. Honan Wu has got the paper out on that. Lots of contributions from older team members like Winbin and the new folks on that effort, including Kevin's efforts to stick in the coupling technology for us to be able to have that talk to the Gamera side and the Geospace side. That model is now open and released under an academic research license for open source usage via the GitHub site that you see there, github.com/ncar/TIGCM. There's a little QR code for it for you if you want to be able to get that to come into play. All right, so that's my suite of overviews about the models. I will happily stop there and answer any questions about models before I jump into the more hands-on, let's get going with the installation process. All right, hearing none, let's jump in. So what I'm going to do now is walk through the installation process and talk about what you need to do the install on the NSF NCAR Derecho system and the NASA Pleiades system. If you want to follow along, I'm basically going to be kind of doing a walkthrough of our installation steps. I highly recommend that you open up the documentation side on Read the Docs. That's Kaiju-Docs with an S www.readthedocs.io. The QR code there should take you right to that site that you can come into play for it from there. So once again, kaiju-docs.readthedocs.io. Scan the QR code if you have a capability to go with it from there. We also have released the code under a BSD 3 clause open source license, and that is also available on GitHub. In this case, it's github.com/JHUAPL. That's the organization there, /Kaiju. The QR code will take you to the GitHub site. It's an open source model. You don't have to have any special permissions to be able to do the git clone process to be able to get after it from there. All right, give me a second to have a beverage. Okay, first step in the install process that we're going to talk about here is getting Python up and running on your platform. You need Python to help us with the build and the run processes that come into play on it. On the NCAR systems, that's as simple as doing the module load conda command. On the NASA systems, the recommended pathway is to actually use this module use -a command to point at some stuff that they've provided for third-party access to packages, and then loading their version of Miniconda 3. If you're on your own platform, you could do download Miniconda. You got Conda, you can do Anaconda. You can go forward with it to get there. On these systems, I strongly recommend using the module load command so that you're using the integrated environment that's available for that system. If you start doing Miniconda and module, things are going to get confused, and you're going to have things that come into play for challenges on that front. Once you've got Conda available, then you want to create an environment for the installation of the tools that we're going to talk about going forward with it here. That's as simple as the conda create command. I'm going to use, and we throughout the documentation use the environment kaiju-3.12 because we're recommending that you use Python version 3.12. The name that you want to use is entirely up to you, whatever convention or practices that you want for that. Maybe you don't want a dot in there, maybe you want an underscore, I don't know. Maybe you want to call it my favorite environment. It doesn't matter. You just need to remember and use that going forward with the install process. Once you've created that Python environment, you want to be active into that Python environment by doing the conda activate command. And then we've worked pretty hard to make the next step work, and that is doing just a simple pip install of KaiPy. KaiPy is the Python tools that I'm going to talk a lot more about at the end of the session here, but it is available via PyPy, and at some point in time we'll do a conda module for it, but we just didn't have time to get it there, and the pip install works pretty well for us going forward. So fairly straightforward first step in the process is to be able to just get a conda environment to go forward with it and then get the KaiPy package installed that. Okay, once you've done the conda environment and you're in that active conda environment, you're going to want to get the software package and software tools to be able to go forward with it. I recommend that you go into a source directory or somewhere like that you want to do. That's why I got the little CD source. That's a little variation that isn't exactly in the read the docs version of it there, but the next step of doing the git clone of the Kaiju repository is there. If you do git clone without anything besides the URL listed there, it will create a directory called Kaiju with all of the software downloaded into it and the repository version that comes into play there. So you're going to want to CD into that process. Once you've got the software downloaded from GitHub, you're going to need to set up the module environment for your system. On the Derecho system, These are the recommended modules that we want to have in here for the environment variables, the compiler versions, being able to have MPI. HDF5 is what we primarily use for output from the Gamera side modules and things like Raiju. NetCDF is what is needed for the TiGCM output files. And then the ESMF is a module that's needed to support the transformations inside of TiGCM. If you're following along on the instructions, I am on the variant pathway for the ability for you to be able to use the modules for doing a couple GTR runs. So you may hear me use that term going out for here, and what that means is that within the Mage 1.25 version of the software that you've downloaded, you could run just the Geospace side with the Gamera and Raiju and the electrodynamics if that was what you wanted to do. But if you want to do the full coupled suite, and we often call that GTR for Gamera, TiGCM, and our Raiju RCM interchangeable in that process there. But these are the modules that make that go forward with that for the process coming into play. You need to use these specific modules, these specific compiler versions, because that's what we've tested and that's what we've found works on the various platform. If you go off and use the standard ones, there may be issues, there may be things that come into play. In particular, it's very important that you use this module set on the NASA Pleiades system because of various compiler issues and the ability to get the module sets to work for the coupling for the TiGCM going forward on that. While not supported here, while not part of my emphasis of the talk, these are the kinds of things that you're going to need to have available to you if you want to compile on some system that isn't these things. You're going to need a compiler, you're going to need MPI, you're going to need HDF4, HDF5, excuse me, NetCDF, et cetera. And you're going to be responsible for getting those going. And unfortunately, we as a team don't have the bandwidth to be able to answer all the questions for supporting installation on various platforms, but you should be able to follow along these instructions for the installation process on the two main supercomputing platforms. Okay, so a fair amount of time later after you've done all of that, then you can go on to the process for doing the build. On the NCAR platform, it's simply just a matter of getting the FC, the Fortran compiler environment variable set there, and there's already a typo I noticed here. It should be export FC equals, not FC equals. That's not gonna work very well, sorry about that. On the NASA Pleiades system, you do need to set up the various environment variables for the compiler, and there are actually two directories that come into play for the path for some libraries that we had to build special. And there's this prefix home 7 nrow3 local 3 the directory that comes in play. That's Nikhil's directory where he has built the versions of ESMF and HDF5, no, NetCDF, and that will work with the compiler versions in the modules that come into play there. The NASA Pleiades system has a pretty strict process for sharing things. We can't make it globally available by default. So if you just email Nikhil, he'll make sure you have access to those module pathways going forward on that. Okay, so you've got the compilers set up, you've got the environment variables set up. What do we need to do to be able to build the code processes? In the source directory where you checked out the clone of the GitHub repository, we recommend creating a subdirectory where you're going to do your build process. In this case, I'm calling it build_GTR for that GTR run that you're going to do. If you're looking at the default directions, it's called build_MPI for doing the build MPI directions. But in that directory is where you're going to do the build process. We use CMake to build the makefile that lets you build the whole process for the models. The CMake command that you do from within your build directory needs to go forward on that. In particular, the allow invalid compiler option is what you need to be able to get things to work for the GTR coupling. This command will dump all that output to cmake.out. You can look at the end of that cmake.out, and it should say successfully built the make files. Okay, once you have a make file, then you can go ahead and proceed with the building of the code base for the Geospace portion of the model there, and that's the simple make -j4 Voltron_mpi.x command. The -j4 actually allows it to do some compiling in parallel because there's a lot of different submodules that need to be built. If you don't do that, it can take up to 15 to 20 minutes if you're just going serially trying to build the thing on one processor after another. We're dumping all of that output into a make a Voltron out file. You should see at the end of that 100% complete modules all built. That gives you the core technology to be able to run the magnetospheric portion of the simulations. There are also several other tools that we have that we recommend building at this time. These are CalcDB, CHOP, SCTrack, and Slice. CalcDB is a tool that goes along and allows you to calculate that delta B, that ground magnetic field perturbation, from the currents that are flowing in the magnetosphere, field line currents from the magnetosphere boundary down to the ionosphere boundary, and the currents in the ionosphere. Chop.x looks at covering in different chops of the files. Slice does different slices for it. And sctrack.x is an executable that will allow you to do interpolation along a satellite track. That works in conjunction with the CaiPi. There's a CaiPi module that will go off to CEDAR web and pull down the relevant portion of data from most of the satellites that we care about, MMS, Geotail, GOES, etc. There's a JSON file there that does that. And we use the sctrack.x file to do the actual interpolation because the grid in the magnetospheric domain is essentially a 3D unstructured grid, and the 3D unstructured grid interpolation in Python and SciPy is really, really slow. And so doing the interpolation with our native Fortran interpolator is much, much faster and actually allows us to do time-based parallelism so we can break it up into chunks and do that interpolation across multiple processors and get that output coming forward with it from there. Okay. So that gets you the magnetospheric portion of the system built to be able to go forward on that, and some supporting tools to go forward with it from there. The last piece that you need to be able to do to get the code bases in place is getting the TiGCM compiled and ready to go for the environments that come into play. So go back to your source directory, wherever that is for you, or wherever you wanted to have the code bases come into play. And then you need to do git clone of the TiGCM repo. So here's an important point for the Mage 1.0 environment. We are, in fact, using two different repositories because of the heritage and the different independencies of the models that come into play. And so you'll clone the TiGCM repo. This is the TiGCM 3.0 repo, and that has in it the capability and the technology to run TiGCM as the standalone module with Helix or Weimer or whatever you want for your high latitude ionospheric specification. Or you can use it in the coupled mode and have that coupling capability to come into play for coupling to the Mage environment. And in fact, to do a full-up Mage simulation, you're going to need both the standalone and the coupled version of the models, which we'll come back to later. Here are the system differences after you're going to use the same module set that I talked about in the beginning, so you don't need to change the modules. In fact, if you change the modules, there are going to be problems because you need to have built the TiGCM code with the same compiler that you built the magnetosphere Kaiju code base with from there. You need to export location for where the various input data files are for the TiGCM space. On the NCARD systems, that campaign directory is open and available. You don't have any issues. If you want to get to the data that we have on the NASA Pleiades system, that same security permission issue comes into play. Just email Nikhil, and we will be happy to share that portion with you. And then it's a build process. We recommend setting an environment variable called TGCM home. That is where you've done your checkout of that for it to be able to go forward with that. Just like you did during the Kaiju build process, we recommend creating a build directory. Right now, things are a little clunky on the TGCM side. You need to do builds for different resolutions at compile time. So we have the TGCM build _Q for what we call quad resolution, which is the recommended resolution for going forward with the simulations with it. From there, go into that directory. And for the build within TGCM, there are a lot of different pieces that come into play and files that need to be set up and structures that need to be moved. And so we've created a Python script to facilitate that process for you. And that Python script is called tygcmrun.py. It comes as part of the TGCM repo, so you'll have it in the TGCM home directory. And there are two commands that you see here at the end. The -OC is for only compile. So that first command is going to compile the standalone version of TGCM. And then the second command, the -OC -CO. CO is for coupling. That's going to create the version of the executable that's designed to talk to the Kaiju portion, the magnetospheric portion of the simulation. These commands will run. They'll take a little bit of time to create your build processes, but then you'll have a set of executables for the build of the system there. When you run this, TGCM creates, I think it's 4 different directories that come into play, and the standard out directory is where the executables will live to come into play. All right, so everybody breathe. You've done a lot. You've done a massive amount of work. Actually, part of the reason why I also didn't want to make this interactive is that these builds can take some time, and we would all have been sitting here and probably be getting closer to 90 minutes after everybody went through all the build processes here to play. But once you have the builds, you can go ahead and get ready to go ahead and do the run of the model going with it for yourself there. You want to move to the scratch space that you have on that platform. Usually on these high-performance computing systems, you have a limited amount of space in your home directory. Don't try to do a model run in your home directory on the supercomputer, because your run will probably crash when you run out of disk space. So you can go to the Glade Scratch on Derecho or the no backup system on the Pleiades thing there. Create a run directory that you want to use. Go into that run directory, and then you need to copy into that run directory the executables that we just built. So the tygcm.exe, which is the standalone, the tygcm.x, which is the coupled version, and the Voltron piece, the Kaiju piece that you built. Copy those into your run directory. So now that you've done all of that hard work, you're actually at a point where you can start to think about doing a run. Yay! You can actually do a science investigation. We've created some tools to try and help with that process to make it a bit more streamlined, so you're not having to edit 5 or 6 different XML input files into the Fortran. And because we're geeky people, and I'm a Star Trek fan, not so much a Japanese manga fan, we have you created scripts called Make It So and Engage to do that process, because as anyone who has been on the enterprise knows, nothing happens until you say engage. So anyway, that's the inside the baseball joke on that front. The engage command that you see right here with the output in the terminal window here, if you run --help, it will tell you which versions of the TGCM run and Make It So, which is the sub piece for the Kaiju space that it's doing there, and give you the output that you need to come into play for it there. It is designed, it leaves behind some JSON files that are the answers to the questions that you used, so that if you go into it and you're like, oh, I want to rerun that, but I want to change just one parameter, you could edit the JSON file, use the JSON file as the input for it for coming into play. And there is a -mode option with basic, intermediate, and expert. We're recommending everybody out here just use the basic. That's what we think are the best default options for running the model. Intermediate gives you more flexibility, more interesting things to get into it. don't run expert without talking to us, because you're going to do things that could potentially break it, or you could end up with results that you don't want to go after it here. But it is available. Our expert users need to have that capability. And I guess that was one other point that I wanted to make on this system here. The engage and make it so is what our team is using to set up our runs. And so we've invested the capability to try to make it user-friendly, but also have the capability to support the development and enhancement of the model. Before I go into the talking about the examples of what Make It So does and Engage does, I wanted to do just a little bit of terminology that kind of comes into play and talk a little bit about best practices for setting up a run. What you see at the bottom line there is sort of the user-defined section for the run there. And that's when we start coupling all of the various versions of the model together and then go through the event that you want to look at. We generally recommend that you do order 12 hours of runtime before the event that you're looking at. I see a lot of people doing runs at CCMC where they're interested in looking at a storm or a substorm, and they start in the middle of the storm or right at substorm onset. The model is not going to give you the answer you want if you do that start at that point in time. The 12 hours is a recommendation. If 12 hours puts you back in the middle of a sudden onset of a magnetic storm, don't do that. You want to be able to think about what you need to do in terms of the solar wind thing there, and that's why there's a little bit of art that comes into play going forward with that. Precursor to your period of interest, the Make It So and Engage and TiGCM run processes are going to do different levels of spin up and warm up for what we're looking at in the model itself. We generally do a warm up where we're just running the Gamera and the RCM to kind of get settled down a little bit of that noise in the coupling that happens for 4 hours before your start time to help with the stability. And even before that, in the Gamera portion of it, we do 2 hours of spin up where we're blowing in solar wind with no magnetic field to kind of help that magnetosphere come into play and take shape that comes into play. Parallel with that, if you're doing a GTR run with the TiGCM enabled, there is some time that you need to get the thermosphere ionosphere spun up for the conditions that you're working at and looking at, and that's this GCM spin up time frame that comes into play. The Engage script is designed to use these defaults to set all those things up for you, so you don't have to worry about it. That run, those pieces will get set up and taken care of for you there. Why are we using those values? That's what we've sort of played around with. Are these the absolute right values to use? We don't know. That's actually part of the investigation. I have an undergrad working with me on that right now, trying to help address those questions. But that's the recommended approach for setting things up here. It is caveat emptor. There is no checking within our software system for the viability of your solar wind file. So we will let you start in the middle of a geomagnetic storm. We will let you start at substorm onset. You have to be careful about what you're doing there. And the CCMC is working. We're talking with the CCMC, thinking about trying to create some stuff that helps try to prevent those kind of scenarios from happening. But you can do the same thing with your runs and your configuration at CCMC. Okay, so what happens when you pop up and you actually run Engage for it? So this is what I've done here, and here is a little bit of an output thing that comes into play. It's going to ask you, first thing first here, about a name that you want to use. The default name is going to be Geospace. You can stick with that if you want, but if you're doing, your favorite substorm or whatever interval, your favorite storm, you're doing the Gannon storm, you might want to use a descriptive name there, and that descriptive name will carry throughout the jobs that are submitted to the supercomputing platform and in the output file names from the results of your simulation that come into play there. Then it's going to ask you that start and stop date. Those are the start and stop dates here of the time frame that you're looking at. Resolution, going to ask you what resolution you're looking at. There are a variety of different resolutions that we support going back from terminology when I was a grad student of double, quad, oct, and hex, where you're doubling the dimensions as you go up from each of those things on the Gamera side. The recommended level, the recommended resolution for folks going forward here is the quad recommended system. It's going to ask you next about which system that you're on, either Derecho or Pleiades. I was doing this test on Derecho, so I answered that. If you do, well, depending on which system you ask, it's going to ask you about the supercomputing account that you want to use. That's my account. You're not going to be able to submit if you don't have that you're in my permission there, and I can't add you to that. I can't support everybody's computation coming into play. That said, if you have an NSF grant and you want to use your NSF grant to support research for doing these kinds of things, you can make a request through the NCAR websites, that I'm blanking on the URL, I should have had it there, for supercomputing time to support your research, and you'll get your own account to be able to do that. You can do that. Similarly, if you have NASA grants and you want compute time to support the research that you're doing there, you make a request to the NASA high-end computing side. My understanding on the NASA side is that when you submitted the proposal, you had to put in an estimate of the computing time that you wanted to do, and then once it's funded, you say that this is funded, and you can get the resources to come into play. I don't know if you can, after the fact, say, oh, I need to do some simulations and get the time on that, but I'm certainly willing to talk to folks and work through that. You're going to be in the directory, the temporary directory that you set up in the earlier step to do this run, so you can just answer dot for the thing there. It's going to find the locations for the software based on the environment variables that we set up, ask you a couple of questions about the queue, and go forward with it from there. There's a whole suite of questions that come into play about different things. For the most cases, you can accept the defaults. Once you go through all of that, you will get to the last little steps of running through the interpolations, getting everything ready to go, and it will come out and tell you that if you want to submit all the job scripts, that there is this simple command that you can run to do that. That is what a successful completion of running Engage will look like. Okay, hold on a second. Let me have a quick beverage. All right, so if you do that run of Engage, this is what you're going to see in the output directory for you to be able to go forward with it here. There are a bunch of .pbs files. This is for the batch system on Derecho. I think it's actually the same batch system on Pleiades, so you're going to see the .pbs files there. You'll see some of these have spin up, some of these have warm up, and then some of them are no name here. These relate back to those spin up, warm up portions of the setup requirements that I talked about in that graphic earlier on that comes into play. The Geospace ones is the jobs that you're going to come into play. This .json file is the output of the Engage process. Here is the shell script that you would want to run to actually do that. I'm lazy, I don't have dot in my path, so I had to do // to be able to get that script to actually run, and then it submits all of the jobs in a contingency fashion so that spin-up has to run before the warm-up can go and go through and get that to go with it, and it'll let you get that come into play. Excuse me. The executables that are in here, some configuration files that are coming into play, and the last file that I will just point out that's worthwhile for folks to know about here is this file called bcwind.h5. Those are the actual solar wind files that the script has used CEDAR to come off and grab and get you the solar wind files that you're running to go forward with it from there. Hit that run command and then wait. If you're on a system like Derecho and it's the week before GEM or it's the week before the CESM conference, you might be waiting a while because there are other people that are using the computer. NASA Pleiades, variations happen there as well. But you will end up within that directory, and I'll come back to this in a little bit, so a whole bunch of output files that we're going to talk about what you want to be able to do. All right, segue with some wonderful AI-supported art. Was that too hard? Was that too much for you? Want to be able to do that? You don't want to go through, you don't want to do all of that stuff. Well, maybe we should talk through what you want to do or how you would go through doing a submission on CCMC for the runs on request. Right now at CCMC, version 0.75 and version 1 are available. We'll be working closely with the CCMC folks in the coming weeks and months to get version 1.25 up. Since they have version 1 up and running, adding 1.25 is really not going to be that hard. It's just a swap out of an individual component there. But to do this, and you can follow along right now if you want to do your own request and do your own run, go to ccmc.gsfc.nasa.gov. And then click on the option over here for the model catalog and select the model catalog. That will bring you to this page that you see over here. In the model catalog piece, you can type in MAGE. It will give you the 2 different MAGE options and then some other models, but MAGE are the first 2 that come into play. Version 0.75 is first, version 1.0. Click on the Submit Run on Request option for that to come into play, and that will bring you to the next page in the run on request process. Is anybody trying to follow along? Should I keep trying to pause for let people to catch up to this? Yeah. You're going to try to, is it going okay? Okay, good, thank you. So the next step is submitting the run on request thing there. Here you need to put in your name and your email address for being able to go forward with it. Then it's going to ask you for a name for the run that you want to do and some keywords. There isn't maybe there's some definitions of the keywords there, but you must have at least one keyword in that thing or your submission will not proceed. And separate your keywords with spaces. Do not use commas. If you use commas to separate your keywords, the page will complain and you have to go forward with it from there. Underneath that, you can select what intermagnetosphere model you want to use. We recommend choosing, if you're doing the RCM there piece, and then to emulate what I was just talking about, on the other side, you want to use the TIE-GCM piece that comes into play. Scrolling down a little bit further, so the piece on the right is scrolling down further on that, and it asks you to input the start and stop time for the interval that you want to look at. I have inserted in here the start and stop time of the default options that I was using for Engage, so it's this... sorry, it's tiny on my screen here. It's a September date, and it's only basically like an hour of runtime there. That bottom box is the total runtime that's coming into play. That will be computed for you from the start and end times that you put forward on that front. Pick your birthday. Pick your favorite day here if you're following along that you want to do a simple little test run. You can select the next button, proceed to the submit, proceed to the next step process. That will ask you a couple of additional questions about it for the solar wind input process, and eventually, once you go through that process, it'll go to a page where you can see the output of the solar wind conditions that are going to be used to do that run for the system there. Once you've got your solar wind and that solar wind file looks good, and here again is where I stress that take a look at this solar wind file. Make sure you're not starting in the middle of a substorm. Make sure you're not starting in the middle of a storm. Make sure that the solar wind looks good, that there aren't a huge number of data gaps. There are other things that come into play. This is where it's incumbent on the user to make sure that the solar wind input file looks rational and works for what goes into the process coming into play. Then you will go to the final step of the process that comes into play for submitting the run. The real key option here on this one is choosing the model output frequency. I believe the default is 240 seconds. It depends on what your needs are for that. We generally run at a 1 minute dump cadence, but a 2 minute dump cadence is certainly worthwhile. to do. If you're doing a simple little test run and you only need to see stuff every 5 minutes, you can choose that option going forward with it there. You can put in some additional text in there, and then this final piece will take you to the page on the right where the submission happens. I do believe, and Darren, you can correct me if I'm wrong, this actually puts it into a queue for some human to actually look at before it actually gets submitted into the process, so that they can check to see if there are special conditions or other things that come into play. Oh, it is fully automated. Okay. So then it'll just actually end up in the queue and go forward with it onto the process. And then you'll get an email that says your run is in process, and then you'll get an email when your run is done. And that run is done time frame may vary depending on what the load is on the process that comes into play. In that email that you receive, you will get a name for your run that you're doing. It will look something like what's on the right-hand side there. Your first name, your last name, and then an underscore, and then the date, and then another underscore with the number of the run that you ran on that day. So if you're doing multiple submissions and multiple things, you could end up with things that look different later. Darren, you look like you jump in. You want to say something to correct me? Nope? Okay. What I'm pointing out here is that if you do this run here and there and you want to do your own more complicated analysis on it, you can request to be able to get the output from it. You go to the simulation runs, search for an existing run, and then you want to do that search on that name that you come into play there, and then you can hit the request for getting the output files. They will tar up all the output files and send you a link for you being able to download the output files going forward with it from there. Yes, Darren?
That also has been automated now and is less human in the loop.
So it should work in a relatively efficient fashion. Darren has done a lot of great work recently implementing that you can use their standard IDL-based visualization, or there are now products that are using our CaiPi tools that come into play. But if you need the data, you can get the data from them from this process going forward. And you can do it for your run or any other run. So if you see that somebody already did the Gannon storm, don't resubmit the Gannon storm. Use the existing run and be able to go forward with it from that side of things. Okay. So you've now done your first run. Yay! Either you built the code and you went through the compile and run process, or you did your request at CCMC and you can go forward with the output files that you got there. Now I'm going to do, the team always thinks I'm really old when I do this joke, but I'm going to do the Julia Child trick. How many people know what the Julia Child trick is? You know what it is because you heard me tell the joke too many times. So Julia Child had this great little trick, right? She's doing roasting a chicken or doing something like that. She would put it in the oven, and then she would open the upper oven and pull out the completed version of it, so you could go forward with it from there, so you don't have to wait for all the compute time, all the other stuff to happen. So we're going to get you some results from runs that we've already done, analysis that's already been in place to be able to go forward, to help you be able to make your own output files, to make your own versions of the magnetospheric quick pick that you see here on the left, and analysis of the TiGCM coming from GCM ProcPy on the right. I guess it's the other way around if you're in the audience. Sorry about that. Before I jump into the tools that come into play, let me just take a brief moment to talk about what's going to be in your run directory after you do the run itself. There's going to be a bunch of magnetosphere kaiju output files. They're going to have names that look like Geospace or whatever answer you gave in that prompt back in the engage process. And then they're .gam.h files. These are the Gamera output files. The Gamera output files have a rather complicated naming convention. There are L, M, and M, which are the number of ways that you've broken down the X direction, the Y direction, and the Z direction in the parallel system. And then the I, J, and K are, this is the second portion of the output for the four pieces that you broke it down in I, etc. You don't need to worry about those names and that parallel decomposition. The CaiPi tools will go look for that file and figure all that out and do the reconstruction to give you in a NumPy array all the data that's distributed in the parallel I/O. We're using parallel I/O so we can keep the code going at a reasonable rate, not waiting for it to come forward with it from there. Other output files from the from the magnetosphere portion is the geospace.mix. This is the output from the mix model, and the geospace.riju. This is the output from the riju inner magnetosphere model. I also put in here, just to remind you and remind myself, that the solar wind file that you used to drive the simulation is the bcwind.h5. That has in it the actual magnetic field, velocity, temperature, etc., that was used to come into play for driving the simulation. On the ionosphere-thermosphere side, there are two files that are created for it. There are two types of files that are created for it. There are the geospace_prim.nc and the _sec. Those are the primary and secondary history files. You in the engage process can specify what you want to have end up in the secondary history files. The primary history files are designed to do the restarts and have the minimal required stuff that's needed to go forward with it. You'll probably end up doing most of your analysis, most of your work with the secondary history file. There are also a bunch of other temporary files and other restart files that are created as the output. Those are in the file. You don't need those for the analysis, but the code needed those to do the completion of the run. And we also actually do output some log information. Generally speaking, they're in star.out for the various executable runs that you've done, or star.o and then the job number. That's the output from the PBS batch process. So if your run failed, there may have been something that happened to the system, and you want to look at those log files for the output. Okay. So now we're really going to get into the hands-on portion of it, and hopefully everybody will be able to follow along for what we're doing. We're going to use CaiPi and GCM ProcPi for that. If you want to install this on your own computer or do your own installation, as I said, they are available on CaiPi and GCM ProcPi, or on the CaiPi and GCM ProcPi are available on PyPi. These are the links that take you to those things there. Pip install of CaiPi, pip install of GCM ProcPi will work for you on a Python greater than 3.10 version, and it will install a whole suite of dependencies. We have worked really hard on the team to create documentation. The documentation is in fact embedded in the code. We're using docstrings and following the Google style convention to create our documentation on read the docs with the Sphinx package. The documentation for CaiPi is at caipi-docs.readthedocs.io, and the documentation for GCM ProcPi is at gcmprocpi.readthedocs.io. There are QR codes for both of those things there. If you're going to try to do the follow along and do the exercises in the latter portion of this thing here, I do highly recommend getting these web pages open in a web browser so you can go forward with it from there. So I'm going to pause just a second to let that happen. All right. So now come into the next piece of the example work that comes into play here. And that is our MAGE analysis notebook. We're running this on Google Colab, and so you should all be able to go to bit.ly/MAGE tutorial, capital MAGE, capital T tutorial, and that should bring up a Google Colab notebook for you. You can also just scan the QR code. I wanted to use the short bit.ly link too because some of you don't have cameras on your laptops that are going to take you to the page that you want from there. All right, so I'm going to drop out of PowerPoint, maybe. I'm going to try to drop out of PowerPoint. Okay, cool, and we do see my screen. So this is the MAGE tutorial notebook that's loaded up here. What I've done is I've put a slimmed down data set for MAGE output on my Google Drive. I had to put a slimmed down portion of it because I don't have infinite Google Drive space, but I wanted to make it available for you. For you to be able to do this, to follow along on your thing, the first thing I actually recommend that you do here is you go over to File and save a copy of this in your own drive. That way you'll have your own copy of it. The changes that you make, that what you have will be available to you. You do not have to do that. You can just follow along, but that comes into play for it from there. For this notebook to work on your system, you are going to have to create a link to the My Google directory in your Google Drive so you can get forward on that. So what you need to do is click on the Mage Collab link here. That will take you to this Google Drive panel that comes into play. You click Organize, you click Add Shortcut, stick the shortcut in your top level directory, and you'll have access to the output files that come into play. I will run through that process right here. I click on it. I may have already done this, so it may, yeah. So I've already done it, so it's not gonna happen very nicely there. So we'll go back to, where did it go? Oops. Yeah, there we go. Okay. It will prompt you. It will ask you for permission to share with your collab, your drive, with your thing there. If you don't give it permission, you won't be able to see the data. So you have to do that to push forward on that. You run the next command. Theoretically. Right, actually, okay, here it goes. So this is the connect. Okay, so connect to Google Drive. It's going to ask you for permission. Even though I've done this 50 million times, every time it asks me, it already says it gave me permission. All right, so there. I've gotten permission. I've gone through that process that comes into play. And of course, the joys of doing a demo, what normally take, okay, yay, it normally takes 5 seconds. It takes a little bit of time for it to go. Google Colab is set up so that if you're using packages that are outside of sort of the standard PyTorch set of things, you actually have to run the pip install for it to be able to go. We're setting up a directory name that we're going to use going forward, and then we're running the pip install. My experience with the pip install on this one is that it's going to run through and do it, and then it's going to need to be done again. You're going to have to restart the kernel to get it to go forward with it. So it's downloading a bunch of stuff, blah, 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 doing the pip install, and eventually it's going to get there. If you're running into trouble and you're following along, raise your hand, and my brain trust over here will jump up and try and help you with that coming into play. All right, so the install is almost done on my side. All right. And then I have to restart the session. Okay. And then we come back to the restart. We go back to the restart of the session. We have to rerun the mount command. This time I should not have to get it prompted for any permissions, and it takes 0 seconds. That's great. I rerun this install command, and it should be super quick to get through, and we're able to move forward with the install of and have the robust version of the code going forward. Did it finish? Yep, all right, it did it. So it installed. The libraries that we're using to do plots here, primarily we recommend, or we're using matplotlib as the primary plotting tool within the process here, so you can import that there, and then we import various portions of the CaiPy package for doing that. There's a bunch of stuff we define in our overarching viz, and then the tools for doing the magnetosphere remix and the magnetosphere pipe. So we're going to import those pieces that come into play. Instructions, what you want to be able to do is to try to be able to go forward with the process here, and we want to import this slimmed down data set, and you set the directory for where you need to go. You set the tag, the file tag name. That is that Geospace option, or in this case, it's gross_RU slim. because it was for Nick Gross's research experience for undergrad's version, the slimmed down data set that comes into play. And then you basically create this object that gives you the ability to import and get into the data. And you hit that to load the data set. It's going to give you a bunch of information. And this is what I was talking about, where it's gone out and found that parallel file and doing the reconstruction, looking at what the data pieces are in there. This is going to take a little bit of time to do the import. It's parsing over the file, pulling some time steps, getting things ready to go. It's also finding the ionospheric portion of the data that's available in the Remix output that comes into play. And it is now done. Who's trying out there? Has everybody been able to get to this far? You're good. Anybody else good? I don't see anybody jumping up and down complaining that they can't do it. Okay, great. You can do any number of steps that you want to go after it. This slimmed down data set really only has 2 steps in it, and I'm just going to, by default, take the last step that's available and use that for making my plots. To make a plot, well, we have a bunch of routines that are available for that. In particular, plot XZ and plot XY that do what the names say to sort of imply that they do. They plot the XZ plane, they plot the XY plane, and you can set the boundaries of the domain that you want to look at. In this case, the X boundary, I'm going to go from minus X of 100 to plus 20, and then minus and plus 60 in the Y, excuse me, in the Z direction there. Fairly standard matplotlib kind of instructions for what comes into play for this here. You need to set up your figure size, create the figure. I'm creating 2 axes, or two subplots that come into play. One for the plot itself, and one for the color bar for the plot that comes into play. And then run the plot routine and return an object that you can go with it from there. And if you run that, you have to define the XY boundaries first before you run that, and then you can run it, and you will get the output for the plot. There you go. A view of the density platform here. I did use the vmin and vmax options to set a limit on the density color bars, because the plasmaspheric density can get pretty high, and everything else you won't be able to see the bow shock, the magnetopause, the magnetotail, the other portions that come into play with it from there. We do try to use some of the better color bars. We're using the Virtus color bar for this thing. If you want to look at bimodal data, like the velocity data that comes into play, you can do a plot of Vx by simply changing the variable name Vx here and change the color map to a red-blue reverse color map. This is where I make my second corny joke, and we are very much a pre-Copernican worldview. The Earth is the center of the universe in the GSM, GSE kind of coordinate systems, and so minus Vx is solar wind that's pointed towards you at the Earth, because the positive X direction points towards the sun. So the minus velocities, the minus 400 kilometer per second solar wind that's flowing out here is that blue color, and then there are flows that are coming into the inner magnetosphere that come into play here. All right, so now for those of you that are following along, I'm gonna make a challenge piece for you, and I'm gonna try to hide the answer to the challenge piece, and that is that you should go ahead and make a plot of pressure in the inner magnetosphere. I have no idea what would happen if you generate that with the AI, if the AI would be able to figure out enough about the chi-pi visualization here, but theoretically you should be able to figure out how to do that by changing what you see here in these precursor things, along with the variable list that is coming into play here. So I'm going to pause and let folks try and do that, make their own plot there for a second, let that go. Okay. Anybody have success? Got a thumb up from my colleague in the back that's doing it following along. Thank you very much. Your plot is probably going to look different than my plot, but the emphasis should be here fairly easily. I decided to change the boundaries on this, so it's a zoom in on the inner magnetosphere. Still using the same figure kind of commands to get the axes plots for the main plot and the color bar. The key here was changing var to P for the pressure. I thought since I was doing plasma pressure, I should use the plasma color bar, but you can do whatever you want for your thing here. And actually point out that you can in fact use logarithmic color scales in the plot systems that come into play, and you can see the plot of the plot here in the plasmasphere showing up in the inner magnetosphere portion of the simulation. All right, so let's talk a little bit about how to deal with, how to use ionospheric data files. To get the thing going, you need to point it at the mix file. So we use that base directory with the tag that we came into from before, the gross RU slim, and then it's just the .mix.h5 file that I was talking about. The mix.h5 files are the ones that have the things there. Open up the pipe to be able to do that, and we're going to tell it we want to be looking for things coming from the northern hemisphere. You can do both northern hemisphere and southern hemisphere. We have a bunch of routines, a bunch of different capabilities that are available for making plots. One that I like is the current option that will actually give you the field-aligned current pattern with the cross-polar cap potential plotted as an overplot on top of that system itself. And my eyes are old. I think that the minus, yeah, they are there. The minus contours, the negative cells have the little dotted lines there, and the positive ones have the solid lines. You got a classic region 1 current system with a little bit of faint region 2 showing up from this case. I think what we're looking at here for these things is just a simple southward IMF condition with no BY and pretty idealized configurations coming into play. This one has got some additional labels that we've put in here for the max and min of the cross-polar cap potential and the max and min of the field-aligned currents, as well as the megaamps that are coming into play. You can look at different parameters that are coming into play that are important for the calculation of things like the aurora. You can set variables, set the max and mins for the independent variables that you want to look at with this dictionary option here, and then choose the plot and pass the energy parameter for that into it there, and it's going to give you a plot of the energy flux that comes into play. Okay, so next challenge question for folks out there. I got to hide that quick because the answer is pretty easy. How would you make a plot of the cross-polar cap potential? Got to pause here for a minute or two to just let folks try to do that one. Like I said, this one's not a rocket science challenge question, just the ion plot with the potential. It's going to give you that default value here with the cells coming in on the colored side of plots for the system itself. Fairly straightforward. And then the last piece that I will just show is that it is possible to create fairly complicated plots, fairly complicated combination plots that you want to be able to do. So if you look back at that first image that I showed you, there was a plot of the magnetosphere with the ionospheric plot inset inside of that. And the process for doing that is using a little bit of matplotlib magic to come up with the setting up of the subgrids for the things that you want to be able to do, make the parameter that you want to plot in your XZ plot, and then do an inset object in there for the subgrid spec to create that subplot for the current object that comes into play, and you're passing it the inset object as the axes object to do the plot on. And one last little piece here where we haven't quite gotten as detailed as we want, there, in order to get the color bar for that was used for the system, you need to use this KV command to get that color bar that we had there, so that you can have the color bars available for both the plasma pressure and the ionospheric current subplot that comes into play there. So that's it for the introduction to CaiPi, except to say that you really, if you want to understand what's available, what we have that's in there, you want to go look at the documentation, online documentation. And I will say in the online documentation, let me drop out of the piece there. If you want to be able to make your own sort of summary plots or do things without having to write all of your stuff from scratch, we have made a whole bunch of command line scripts that are available to you once you've done the installation. In particular, if you do msphere pick, that plot that I showed you earlier on, is there a plot at the end? No, there isn't. msphere pick command, and all of our commands have the -h option or minus help option to give you that. That will create the image that was in my PowerPoint presentation. Where did my PowerPoint presentation go? Oops. No. Anyway. Okay, sorry, I can't find the image. It'll generate the summary plot with the RCM inset on the left and the field line current inset on the right. 28, thank you. Nope. Yeah. Maybe. Oh, am I in the wrong presentation? Yeah. Here we go. Yes, I was in the wrong presentation. Sorry. That msphere pick will generate this image here, and in fact, also in msphere pick, there is a minus vid option that will create a video. It will loop over all of the time steps, create individual frames, and then use FFmpeg to create an MP4 file from that. And the last piece I would say on that is that if you have a really long run and you want to create a video in a reasonable amount of time, and you're on a platform with more than one CPU, you can use the minus CPU options, and it'll thread that up and then build the reconstruction movie from the files after all the individual pieces are done. So there's some parallel processing that's available with it there. Other command scripts that may be useful are mixpick and the SW pick will create a plot of the solar wind from that BC Wind H5 file. All right. So that is the kaiju plotting routines. Let me show you, spend a little bit of time talking about what you want to see for dealing with the GCM ProcPi thing there. So for that one, I do need to go back to my presentation here, and I'm just going to leave this in this mode here just to make it a little bit easier. This is the notebook for the GCM ProcPi tutorial. There's the QR code that you can scan, or you can do bit.ly/GCM procpi_GTR Raiju. Sorry, that one's a little bit of a mouthful. bit.ly GCM all caps procpi_GTR all caps Raiju AIJU to get there. I'll give folks just a minute or two to scan that QR code or type in the link to their to the system itself available. All right, so similar process in this notebook to the previous one. Here we have made the entire output of the standard run or the default run that you would get if you ran engaged and just basically hit return 15, 20 times and had it go out from there. And you need to create the link to the CEDAR gem tutorial on your piece there, following that same process that we did before about organizing and adding the shortcut. Once you've done that, then you need to create the connection to the Google Drive piece for it there. I don't know if this one's going to ask me to do the permission. Yep, and connect to Google Drive. I think the first time you do it on the notebook that you actually have to go through this permission process every time. Sorry about that, but security is good. All right, so now that we've got the Google Drive mounted, here we do the pip install for GCM procpi. This one works a little bit better than the KaiPi one for reasons I don't yet fully understand. This one is just going to complete. We're not going to have to do the restart and rerun it in this one, although we do need to restart the kernel, which will happen once it completes with this kernel shutdown command here in just a second. Let me make sure this thing actually ran. Yep. Okay, so that actually ran. So then I run this, and it restarted the kernel. So now that the kernel has access to a version of Python with GCM procpi in there. Here we're going to need to be able to import the GCM procpi tools. We recommend GY as the version of it, similar to NumPy as NP, but you can do whatever you want. Run the OS option to come into play, and then get the code base to be able to point to the data from the process that comes into play. And it's going to load the data sets, give you a few little warnings, but this will parse over and give you information about what is in the output files. Sorry, this is not a slimmed down data set, so this is a full 1 hour kind of thing, and so it will take some time there. And it's a bit slow on Google Drive when you're doing the Google Drive remote things. If you're doing this locally, this process would be much, much faster. Uh-oh. Just run it again. Bad mic. All right. If you want to, you can find out some basic information about what is available for the data files. There are some simple commands that do this. This time_list with the data set will tell you about the time steps that are available in this thing here. I'm only showing you the first 5. If you do the full thing, it'll give you all the time sets that are timestamps that are available. You can find out the variables that are available in here. The ones that are in capital letters are the sort of recommended things to go after. These are secondary pieces that are available primarily for the running of TiGCM. to get information about a particular variable, like what the heck does tn mean, if you do the var info command and pass it the variable name, it's going to give you the attributes that it is the neutral temperature, it is in units of Kelvin, and it is across all the times, levels, lat, and longitudes that come into play for it in the process itself. I'm not sure why it did it twice. Oh, because there's two files. So the output is, the same file exists in both outputs that comes into play there. If you want to find out what pressure levels are available, you can do a similar command with this level list to get it out here. The idea is that there are some pretty simple commands that help you do some basic understanding, exploration of what's available, what's in the output, in the netcdf output files to come into play. All right. Latitude and longitude, and latitude and longitude. So you can see that it's going from minus 88.75 and minus 180. All right, enough about the what grids are we on? Let's actually go ahead and make a plot. So you need to do this inlining command to get it to create reasonable high-end parameters there for what happens there. And then the data set variable is what was going to be passed to these things, which variable you want to use, what time you want to do, and since we're going to do a profile plot, we need to specify a particular location, so 30 degrees and 45 degrees, and you run the GY plot level variable command with the variable names and the latitudes and longitudes passed to it, and you get an electron density profile. And yeah, you've got like an F2 peak here at the pressure, or an F peak there at the pressure, and you can see how the electron density is varying. All right, whoop, gotta hide my hints in my solutions. Oh, I opened the hint in the solution. Bad mic. Okay, the challenge. What is the density peak look around Des Moines, Iowa? And as the signs tell me, the S's are silent. So anybody seen those signs around town and tried to figure out what that meant? Nobody, okay. As a hint, for those of you that need to know, the latitude and longitude of Des Moines is 41.58, blah, 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 and 93.61, blah, blah, blah. I assume somebody went on their phone and found the GPS coordinates, probably of the Iowa Convention Center here, but anyway. All right. Pretty simple process to be able to do that. You just need to replace the thing with the actual variables, the latitude and longitude variables that are close to this thing here. It is not doing interpolation, is not doing guess. You have to give it actual variable values that correspond to the latitudes and longitudes that are available in the data set. But if you run it, you'll get a profile for Des Moines, which looks somewhat different than the 30 degrees, 45 degrees plot that we were looking at earlier. We have a whole suite of different kinds of plots, standard plots that are available for folks to go after here. Here's a lat-long plot that comes into the system here. We've tried to add some labels about here for the max and the mins, what the temperature ranges are, what pressure level you're looking at, roughly what height that pressure level corresponds to, and a range for the color bars that come into play. This is what a generic plot does with the simple little value system coming into play. You can augment these plots. We underneath are using CartoPy for a lot of our analysis for being able to handle with the geographic features. CartoPy has a lot of nice features, in particular the coastline, so you can draw the boundaries of all of the individual objects. The nightshade objects, so you can see where it's day and where it's night, that comes into play. And I'm not exactly sure how NiCel implemented this, but we also have the ability to get the geomagnetic equator on there that can be particularly useful if you're wanting to reference, some certain ionospheric features that are correlated by the magnetic system rather than the geographic system that comes into play. I don't think geomagnetic equator is a default CartoPy thing, so he must have done something clever for that one. We don't remember. But anyway, the geomagnetic equator is there, and that looks like the geomagnetic equator. And that process will give you the geomagnetic equator. And just to show that it works, it'll come up with all that for you there. All right. A challenge question for you: what does the density look like at pressure level 0? Basically, a lot of cut and paste processes here. Change the variable and level parameter in the plot above, and if we do that, you can change the variable name to NE and the pressure level to 0, and you'll end up with a plot that looks like this. And you can see the organization by the geomagnetic equator coming into play here. Another type of plot that is available as a standard suite of plots in the system is pressure level versus longitude. So what does it look like going up above you at at longitude range here? So here's the plus or minus 180 degrees of the electric potential, and at a particular time, and that plot comes into play. It looks like that. And then also have latitude versus time, so you can look at the evolution of the system over time as a function of the latitude that's available in the parameter from itself. Generally speaking here, I'm going to urge you to go look at the documentation. The convention is plot underscore lat long time, and the variables there. Pretty much, I think all of the kind of plots that you would want to do for basic analysis, even advanced analysis of the output data comes into play. It's available from this notebook and the API. Okay, it's being slow. Oh, my session crashed for an unknown reason. Well, that sucks. Oh, okay. So it's still thinking. Come on. Oh, this is because it's a versus time, so it's having to read in across all of the data files to get the slices to be able to do that, and it put that into the NumPy array that's available to you for the analysis. So that kind of analysis, that kind of thing will take some time to compute and to happen there. So that's the overview of the GCM ProcPy thing here. I will also point out on the GCM ProcPy process here that we have various command line scripts that you can run to be able to get pieces there, the ability to generate movies. And actually, Nikhil has invested a fair amount of time and developed a GUI interface so that you can go in and move around, zoom around, and be able to plot things on your own from the GUI. The last piece I will highlight here on the GCM ProcPy side of things is that this tool works not only with the TiGCM output files, but also with the WacomX output files. So if you attended the tutorial yesterday on how to run WacomX and you wanted to be able to look and compare stuff from this run to something you did with WacomX, you could use GCM ProcPy to have both data sets available to you in the same NumPy arrays and the same plotting routines to give you nice looking figures. All right, so let me jump back into my presentation. Where did my presentation go? That's not it. Sorry. There we go. Okay, so I'll jump back into my presentation to sort of just get down to my last slide here of we are very much looking forward to working with all of you. The team worked really, really hard to get Mage 1.25 available as an open source release so that you can do your own runs and contribute to the development of the model itself. 1.25 is a science beta, so before you go off and do a publication on that, you definitely want to talk to us and do that. And there may be quirks, there may be features, so we really would appreciate feedback of this isn't working or these kinds of things. Please look at the documentation first, but move forward on that. And we really look forward to the opportunity to work with you going forward. And I've now talked for almost an hour and 45 minutes, so you're probably sick and hearing my voice, so I give you early release to go to lunch unless you have questions, and I'm happy to take those. Do you have a question? Oh, I don't know if we have microphones here or not either. Oh, there's one over there. If somebody has, yep. Oh, don't fall. Don't hurt yourself, please. Any questions?
Maybe I didn't need to come over here.
Oh, sorry. Didn't mean to make you trip.
I have a question for you.
Yeah.
So I plan to be working with some undergraduate students next year, and I think being able to run simulations from anywhere that's not in like a whole R1 facility kind of like school kind of thing is really important for people who are just getting started.
Sure.
Are there any resources that you have? Like this tutorial talk is great, but I don't think this tutorial talk is approachable for somebody who has like just touched Python like a year ago or something like that. I know you had mentioned there was all this stuff on the Read the Docs. Is there some sort of thing that you've created that makes it approachable for newer people who might be intimidated by this?
Yeah, so we're working on that. I just had I have an undergraduate working with me this summer, and she just learning Python, and so we're trying to get the pieces into play. There are a few bugs, a few quirks, a few things that we've improved based on that interaction, but we haven't quite gotten it all in place. The Colab notebooks are I think a good starting point. What I would actually say for you is that if you're interested in doing something with the students, and in particular as part of a class or classroom REU kind of experience, we can get you set up with an allocation and account for the classroom on the NCAR system. And that comes with two advantages. One, they can actually start getting onto an actual environment and go through building and doing and learning how to do all of that. And I agree that can be a little bit challenging, but I think worthwhile for them going out into the experience there. And they'll have computing resource allocations that come into play, which gives them the Jupyter. We have a Jupyter Hub system set up there, and it talks directly to the file system, so that there isn't this big long Google delay for getting to the system there. So that you could begin to tailor an environment, tailor an experience, I think, in that combination. And if you're interested in doing that, come talk to me afterwards, and we can try and set something up and build something and make it.
Yeah, and just to sort of clarify, this is like provided by NCAR to institutions, like free of charge, that kind of thing, right?
Any institution that wants an HPC allocation for a classroom experience, and it doesn't have to be this. It could be you want to teach computational fluid dynamics, and you want to have them run on the computer. Whatever it is, as long as it's an educational rated experience for a U.S. institution, go to the NCAR Sizzle page and ask for a classroom allocation. And there's a process that's very straightforward, and they're very willing to help.
Okay, cool. I'll probably set something up with you later.
Great. All right, well, thanks everybody for sitting here. Hopefully it wasn't too painful. Hopefully you got the opportunity to do a little bit of your own plotting. Thanks to those of you that followed along. I'm gonna close out the Zoom session, shut this down here, but I'll be available at the front of the room for anybody that wants to ask any follow-up questions. Thanks.